Welcome to Integrated Math 3, Notes 8-1, Square Root Functions. We're on page 103 of the book. Let me zoom in a bit. As we begin these notes, you notice I have a stack of paper behind my notes. So it would be a good idea for you to take out some extra paper so that we can put our key ideas like Cornell Notes style over on this second pieces of paper. All right, also, as you're taking notes, if there's something that doesn't quite make sense to you, you should pause at that point and go back and look at it again and see if you understood what I said the second time. And if not, make a note to yourself to ask me about it in class tomorrow. All right, so the learning target today. We are going to graph and describe transformations of the square root function y equals square root x and interpret key features of a graph that models a relationship between two quantities. Okay, so before we begin, I'm going to go back to the first target, which is to graph and describe transformations of, this time it's going to be a square root function. So I'm going to go back to previous knowledge that you should have from Integrated Math 2. So from Integrated Math 2, what we learned was something called transformations of functions. And this is called, it's the family of functions. All right, so back in Math 2, what we saw was we had a parent function for a quadratic, right? Y equals x squared. This is for a quadratic function. And we would graph the parent for the first time by making a t-chart. So we would pick values for x, and then we would see what our output values were for y, like -2, -1, 0, 1, and 2. When I would input those into my x squared function, I square a -2, it becomes 4, a -1 becomes 1, 0 squared is 1, 1, and then 4. And then we graphed this parent function at 0, 0, -2, 4, 2, or sorry, 1, -1, 1, 1, 1, and 2, 4. And this was called the parent function. And the parent function for quadratics is always this parent. This is f of x, or y equals x squared, our parent. Then what we saw was that there were certain features of an equation in vertex form, and remember vertex form for a parent, or for a quadratic, was y equals a, x minus h squared plus k. And so our a value would scale, and it would also reflect across the x-axis. And we knew this if a was negative, it would reflect. And the scale, it would depend on if it widened or narrowed. The way we could tell is that if absolute value of a was larger than 1, this would be a vertical stretch or narrow of the graph. And if absolute value of a was between 0 and 1, this would be a vertical compression or a widen of the graph. And then our h value and our k value, h was left or right, shifting, right, left or right, opposite of sign. And k was up or down, and that was the correct way, right? No opposite of sign. Okay, so now we're going to use that same idea on square root functions. So it says the whole speed, h, in knots of a boat is given by the function h of x equals 1.34 square root x, where x is the length of the boat in feet at the waterline. It says the hull of the boat is the body of a boat. It is measured from the front of the boat, the bow, to the back of the boat stern. The hull speed formula is derived by analyzing wavelengths as the boat displaces water as it moves. Okay, so now here's our hull speed, right? And here is our first question. The hull speed of a function is a transformation. It's a transformation of the parent square root function, f of x equals square root x. So off to the side, we're going to make a note. Our parent is f of x equals square root x. Or you could say y equals square root x. It says graph h is this function, and f is this function on the same axis. How do these graphs compare to each other? All right, so to graph this, let's go ahead and on a separate sheet of paper, let's see what the parent square root function is going to look like. Okay, so here is number 1, and we're on page 103. All right, the parent is y equals square root x. So we're going to build our parent. We've never seen this before. We're going to graph it by making a t-chart. Okay, so our values that we can pick for x. Let's pick some values like -4, -3, -2, -1, 0, 1, 2, 3, 4. Let's go ahead and pick those values, and we're going to substitute them in to our square root function. So y equals square root -4. Now, the square root of -4 is 2i. This is a complex number. Therefore, it will not exist on the real axis. Well, the same way, this is going to be a complex number, and this one, and this one. So we cannot graph any values for which x is negative. So we will have to begin at 0. Y equals the square root of 0, and the square root of 0 is 0. Y equals the square root of 1, which is 1. Now, square root 2, in order to square root 2, we would need a calculator because 2 is not a perfect square. So I'm going to get my calculator out. And I'm going to say square root 2 is, it's about 1.41. Square root 3, same thing, right? Y equals square root 3. I would need a calculator, which is 1.73. And then the square root of 4 equals 2. So based on this, I can see there's certain values I would want to avoid choosing. I really wouldn't want to try to graph this value or this value. They'd be a little bit difficult to graph. So based on this, I can see another good value to choose for x would be maybe 9, because 9 is a perfect square. The square root of 9 is 3. So now I'm going to modify my parent function so that I have only values that are easy to use. And so the first value that I would pick is 0, 0. The second value would be 1, 1. The third value would be 4, 2. And the fourth value would be 9, 3. And we're going to graph those values on the previous page. So I'll do my parent function in green. So 0, 0 is right here, 1, 1, 4, 2, and 9, 3. Whoops, 9, 3. Right there. There is my parent. Y equals square root x. Now, for my new function h, right, my h function is right here. So I will also do that on a separate sheet of paper. I'm going to take my original values from my parent, right, x, and then y equals 1.34 times the square root of x. And what I will do is I will take my original values, 4 and 9, and I'm going to now multiply each of my output values by 1.34. So my output was 0, my output was 1. So what I'm doing is multiplying by 1.34 all of my original square root values. My output was 2. My output was 3. This gives me 0. This is 1.34. This is, I'll use my calculator, 1.34 times 2 should be 2.68. And 1.34 times 3 is 4.02. And these are my transformed function values. All right, let's go ahead and graph these. So graphing them, I will have, I need to move this off to the side. So I have 0, 0. Oh, I'll do this one in pink. That way you can see the difference. So 0, 0 is the same. Then I have 1, comma, 1.34. So I'll graph 1, comma, 1.34 would just be about right there. And then I have 4, comma, 2.68. So 4 and 2.68 would be all about right there. And then 9 and 4.02. So 9, comma, 4.02. And this is my transformation. H of x equals 1.34 square root x. So it says, how do these graphs compare to each other? So if you were making a comparison regarding these two graphs, what would you say? I would say, let's see, this one is getting taller, right? It's getting stretched upward. It's a vertical stretch. So I would say that this graph is a vertical stretch from the parent function. So h of x is a vertical stretch of f of x equals square root x. Now I could have predicted that that was going to happen because if I look back at my family of functions, right, my family of functions, and this is true for all functions, my a value does the same thing in all functions. My a value will stretch or narrow, stretch it narrows in a quadratic, but it stretches vertically if the value of a is greater than 1. And it did vertically stretch my graph. If we look back, the graph is now stretched upward from the previous function. And so you could see that a value was actually right here. A was 1.34. So since a equals 1.34, which is greater than 1, we have a vertical stretch. A vertical stretch. All right. Next, it says, what are the domain and range of f? Okay, so remember, f is this one, the parent, the green one. Write your answers as inequalities in set notation and in interval notation. Okay, so the domain and range for f, again, the green graph. So the domain is all your values of x. So the domain is your x values. And so for x, to the left, the lowest value, or the farthest to the left this graph goes, is from 0 less than equal to x. And to the right, it's going on forever. And so we would say to infinity. And remember, we never use an equal to on infinity. That would be inequality notation. Set notation. Set notation would be from 0, hard bracket because it does reach 0, comma, infinity. Infinity, it'll never reach it, so we always use a soft bracket. And in interval notation, I'm sorry, that's interval notation. This is interval. So this is an inequality. This is interval notation. And then we'll do set notation. So set notation, we basically take our inequality notation and we use the brace and we say x such that 0 is less than or equal to x is less than infinity, and then we close our brace. That is our domain. All right, our range. So remember, our range is for our y values. So we're looking at how far down on the y-axis this graph goes, and it goes to 0. It does touch 0. And then on the y-axis, how far up it goes, well, it's going upward slightly forever. It's going to the side faster, but it's definitely going to go upward forever. It's rising forever. So we would say y, and then to infinity. And then this is, again, this is set, right? We're going to do interval notation. Interval is from 0, comma, infinity. Again, same thing, hard bracket, soft bracket. And then the range would be, in set notation would be y such that 0 is less than or equal to y is less than infinity, and then close your brace. All right, and you notice that off to the side here, they did say to graph the parent square root function, use key points with x values that are perfect squares, such as 0, 1, 4, and 9, which is what I did. I did explain why we would pick those values. And then next it says that we're going to model with mathematics. It says, given that x represents the length of the boat, should the domain of h of x be more restricted than f of x? Can you determine the domain precisely? Explain your reasoning. Okay, so it says x represents the length of the boat. So should the domain of h of x, right, the pink graph, be more restricted than f of x? So let's think about that. The domain of f of x is from 0 to infinity. Now, the domain of h of x, could the domain, if x is the length of the boat, could the length of the boat, x, be 0? So could the length equal 0? No, it could not. No, otherwise it would not be a boat. Obviously. Also, it says that the domain goes on to infinity. Now, could we have an infinitely long boat? So could the length x approach infinity? No. Obviously, there is a maximum value. I mean, you could build a very, very large lengthed hull, but in real life, how practical would that be? Okay, so then it says, could you determine the domain precisely? Explain. No, we could not. And I already said why. No, we cannot, because I don't know the longest boat that we could build. I also think the smallest boat that we would build would depend on what we're trying to carry. All right, let's move on to D. Explain how do you write square root x using rational exponents. So this goes back to Math 2 as well. So back in Math 2, a rational exponent. So rational exponent. This is for D on page, 1D on page 103. Rational exponents. The word rational means ratio, right? Ratio is a fraction, like a to b. All right, so a rational exponent is something like x to the a over b. And so back in math 2, what we saw was, excuse me, what we saw was that the definition of a square root, like square root of a, and then m and n, right? The definition was that this could be rewritten as a to the m over n, always. So this definition or property, right, you must know it. So for example, if you had the square root of 9, you could rewrite this as 9 to the value there is a 1, so 1 in the numerator. The value here is a 2. We don't write either of these, so it would be 9 to the 1/2. Or for example, if you had a to the a squared to the cube root power, this could be rewritten as a to the 2/3 power. Always, this is my exponent, this is my index, so you must know this. All right, so using these properties, we're going to go back and look at how to write square root x using rational exponents. So the square root of x, the exponent here is a 1, and the index is a 2. So we would rewrite this as x to the 1/2 power. And it says to write h of x using rational exponents. So remember that h of x was 1.34 square root x. So to write this with rational exponents, we would say this is 1.34, and then we're going to rewrite x. Square root x is 1/2, so x to the 1/2 power. And that would be it. And remember, in this expression, only the x is being raised to the 1/2 power. The 1.34 has its own exponent. We don't write it, but it's a 1. Right? At this point, I would say you need to pause your video. I'm going to actually stop this video because it's 22 minutes. So at this point, we're going to pause. I encourage you to reflect back on the first page before moving on. And then I think if we look on the back, we're going to have a try these. Oh no, we're going to have some more. We're going to follow up on this. So I'm going to encourage you to pause your video. I'm going to do the same. Go back, reflect on page 1 before moving on.